Hello, I am Kanav. Today I will be presenting LLAMA, a low latency math library for secure inference. This is a joint work with Deepak Kumaraswamy, Nishant Chandan, and Divya Gupta. Let's understand the problem of secure inference. In secure inference, a server starts with a model M and private weights W, and the client starts with the model input X. We want the client to only learn the inference output M of W, X, while the server learns nothing about X. This problem can be solved using cryptographic technique of secure computation, or more specifically two-party secure computation, 2PC for short. There has been much work on improving the efficiency of these protocols recently. The biggest bottleneck towards the adoption of secure inference protocols is the high communication costs associated with them. Consider a simple 7-layer CNN over CIFAR10 dataset as an example. Even for this very simple model, Cryptflow 2, the current state-of-the-art 2PC CNN inference library, costs 340 MB of total communication, 10 seconds of runtime in 345 communication rounds. Delphi focused on moving the bulk of total communication costs to the input-independent offline phase. This model, also known as pre-processing model, is very interesting, as the parties can pre-compute and store some input-independent key material beforehand, and when they have their inputs ready, they can perform inference faster. Even then, Delphi communicates 196 MB in the online phase in 2.7 seconds of runtime. Furthermore, consider an example of RNN on Google 30 dataset. Here the situation is even worse due to mathematical functions like sigmoid and tanh, which are expensive to calculate securely. Siren, the current state-of-the-art inference library with support for such precise math functions, communicates 415 MB of total data and runs in 37 seconds in nearly 60,000 rounds. In our work LLAMA, we use a technique of function secret sharing to reduce the online costs in the pre-processing model. We achieve up to 48x reduction in communication and runs 19x faster in these examples. Let me draw out the structure of the talk first. We start with a brief description of function secret sharing and 2PC using function secret sharing. Then we discuss the drawbacks of existing works and how LLAMA addresses those. We start the technical part of our talk with bit-width changing gates. Then we discuss how we create protocols for mathematical functions using spline approximations. Finally, we discuss the benchmarks we ran using LLAMA and how it compares with other works. FSS was introduced in 2015 by the work of Boyle, Gilboa, and Ishai. It allows a dealer to split a function f into two functions f0 and f1 such that when applied to the same input x, the two functions return secret shares of fx. The security requirement states that each of the f0 and f1 hides f. These f0 and f1 are called FSS keys. For this to be practical, these keys should be also compact in size. In 2019, Boyle, Gilboa, and Ishai provided a way to realize 2PC in trusted dealer model using FSS. In this, the dealer provides input-independent correlated randomness to the two parties. This dealer can also be emulated as an expensive 2PC. Then, using this key material, round and online communication optimal protocols for many functionalities are known due to previous works. These functionalities are called FSS gates. Each FSS gate costs online communication of 2 times the output bit length of the functionality. That is, each party sends an output element to the other one in just a single round. There are a number of works on secure computation using FSS like BGI-19 and BCG plus 21. Aryan is a work which considered the problem of secure inference using FSS, but these existing FSS-based solutions had some drawbacks. First, all of them lacked support for precise math functions, like sigmoid and tanh. As we saw, RNNs make heavy use of these functions, and to support them, we need protocols to securely evaluate these math functions. Due to transcendental nature of these functions, exact evaluation is not possible in finite bit width, and error bound is measured in terms of ULPS error. There are some works in secure inference, which, like SecureML, which provide math functions, but they suffer from high ULPS error. Repeated use of these high error implementations can lead to wrong output with a large probability. Second, most existing MPC frameworks don't support mixed bitwidth operations. While most ML models perform inference on floating point numbers, MPC frameworks operate on fixed point numbers. Existing state-of-the-art float-to-fixed quantizers like Shift-Tree and TensorFlow Lite use low bitwidth fixed point representations for efficiency reasons. Simple computations like multiplication required increased bitwidth of the intermediate output variable to prevent overflows. Without support for mixed bitwidth operations, the existing works are forced to operate on higher bitwidth, resulting in bad performance. Finally, the only prior FSS-based secure inference library, Aryan, uses protocols for ReLU and truncation that are only probabilistically correct. Since the error is inversely proportional to the bitwidth used, they are forced to use higher bitwidth. Also, as the number of ReLU and truncation increases, the probability of overall computation being incorrect increases. In LLAMA, we address all these drawbacks. First, LLAMA supports precise computation over low bitwidth inputs by supporting mixed bitwidth operations to calculate intermediate variables in higher bitwidth. Second, we provide a low bitwidth spline approximation for math functions with a maximum error of 4 ELBs and provide FSS protocols for these. Third, unlike Aryan, our protocols for ReLU and truncation are correct. ReLU and comparisons are taken from the previous work of BCG plus 21 and we use them to build secure protocols for max pool, average pool and argmax. Finally, we integrate LLAMA as a cryptographic backend to EasyPC, creating a complete end-to-end inference system. Distributed comparison function, abbreviated DCF, is a very fundamental FSS scheme to perform comparisons. Here, the function returns beta when x is less than alpha and 0 otherwise. The FSS key for DCF hides these alpha and beta parameters. We call this FSS key DCF key. BCG plus 21 provided an optimized construction for DCF. We start our technical discussion with a brief description of bitwidth changing FSS gates. As the name suggests, they change the bitwidth and scale of fixed point numbers. First, we have an extension gate which increases the bitwidth of a number. Second, we have a truncate reduce gate which reduces both the scale and bitwidth of the number. Both of them need one DCF key and since they are FSS gates, they take one round of communication. As we saw earlier, we need math functions like sigmoid and tanh to support RNNs. Siren, the state-of-the-art prior work which support precise math functions, uses Goldschmidt's iteration to estimate this function. But this approach is not ideal in FSS as it would require a round for each iteration. Our first design choice is to use piecewise polynomial, also known as splines approximation, as we have FSS gate for it due to previous work. Let's understand how the evaluation of splines work. Consider a 6-piece spline as shown. We want to evaluate input x on this spline. We first find the spline interval in which x lies and fed the corresponding polynomial coefficients. This step requires comparisons. And then we simply apply this polynomial to the input x. This step requires multiplications. BCG plus 21 devised an FSS gate for uniform bitwidth spline, which means that all input and output numbers and all the intermediate operations happen in the same bitwidth. They were able to achieve this in using a single DCF key. But suppose we want to apply spline on a low bitwidth input. If we use the spline of the same old bitwidth, we fear overflows due to multiplications, which would eventually lead to high ELPS error in math functions. Using spline of bitwidth just enough to prevent overflows is bad as well, because it leads to high key size and large runtime. Hence, we need mixed bitwidth splines where the intermediate multiplications happen over large bitwidth to prevent overflows. Now, to quickly devise a protocol for mixed bitwidth spline, one could use FSS gate for extension to extend the input value to bitwidth just enough to prevent overflows, and then pass this extended value to the uniform bitwidth spline from BCG plus 21, and finally adjust the output to decide bitwidth and scale using truncation. This serves as a good starting point on which we now present two optimizations. Our first optimization is based on the observation that the coefficient finding step does not need the input to be sign extended. Comparisons can be done in original smaller bitwidth. So we pass the original smaller bitwidth input in the coefficient finding part and use the sign extended input only in the polynomial evaluation. Hence, we reduce the DCF key size. In case of sigmoid, this leads to 4x reduction in key size. Our second optimization is based on the observation that most of the output of DCF evaluation in the spline protocol is discarded and only some part of it is used. Here is the original protocol for uniform bitwidth spline from BCG plus 21. To quickly verify this claim, observe that we are generating m squared values here above, while we use only 2m of these values here. Here m denotes the number of intervals in the spline. To prevent this wastage, we found a way to partially evaluate DCF, leading to reduction of PRG calls by a rough factor roughly of m by 2. In sigmoid, this factor is roughly equal to 10x. The best part of all this is that both of these optimizations are composable with each other. Overall, we get a 4x reduction in key size, 4x reduction in dealer PRG calls, and 40x reduction in evaluator PRG calls in sigmoid. We also propose many FSS protocols for functionalities in inference like convolution, ReLU, and maxpool, but we skip their discussion due to shortage of time. We evaluated LLAMA on a number of benchmarks and compared with existing works. We ran these benchmarks on both LAN and WAN setting. We present some of those numbers here in LAN setting. We compared the fast GRNN model on Google 30 dataset with Siren and observed 48x less communication, 19x less runtime, and 22x less communication rounds. We compared our work with Delphi, which focused on online-offline split on a simple 7-layer CNN. We observed 23x less communication and 5x less runtime. Finally, we compare with Aryan on ResNet 18 model on Hymenoptera dataset. Note that we don't have math functions in this benchmark. Here, even in the presence of correct ReLU and truncation protocols in Llama, we achieve 3x less communication in 1.7x less runtime. We attribute this improvement due to ReLU being a 2-round protocol in Aryan compared to an FSS gate in Llama. This marks the end of Meta. In conclusion, Llama proposes an FSS-based solution to the 2PC secure inference problem in pre-processing model. While Llama aims to reduce the online complexity, it remains an interesting problem to reduce the large offline communication costs, mainly due to large DCF key size. Reducing the size of DCF keys can be an interesting problem with impact greater than just secure inference. Thank you.